We will continue our discussion on the relativistic quantum mechanics. We were talking about the relativistic notations and some of the how to combine the time coordinate time parameter and the spatial coordinates in a single entity called a 4 vector and how they transform under coordinate transformations. Let us start with differential operators. So, let us consider differential operators in relativistic notation. So, in three dimensional case, we have gradient defined as dou by dou x along the x axis, dou by dou y along the y axis and dou by dou z along the z axis. And the 4 dimensional generalization of this can be written as dou by dou x mu, which is dou by dou c t, which is our zeroth component, and dou by dou x 1 dou by dou x 2 dou by dou x, which is dou by dou x, dou by dou x, y, dou by dou y, dou by dou z, etc. Or I can write it in a way which will separate the time component and the spatial component written as the gradient. This is one way of doing it, and the other is with mu as a subscript on the x, which is basically a x mu covariant. So, if you take the derivative with respect to the covariant x, then you will have dou by dou c t, dou by minus x, dou by dou minus y, dou by dou minus z, because the spatial components of x mu covariant is minus x minus y minus z, and this is essentially dou by dou c t minus gradient. Let us look at how the dou mu dou x mu transform under coordinate transformation. We know x mu goes to x prime mu, which is a mu nu x nu, and x covariant goes to x prime covariant mu a mu nu x nu. Dou by dou x mu contravariant will go to dou by dou x prime mu, which is equal to dou by dou a mu nu x nu, which is equal to, I can write it as 1 over a mu nu dou by dou x, and this 1 over a nu mu is essentially mu nth component of the A inverse matrix times dou by dou x nu. But we saw in the earlier lectures that A inverse mu nu is essentially equal to A mu nu dou x nu. This is basically the way a covariant vector transform from our previous lecture. So, previous lecture says that this is the way a covariant vector transform. So, this says that dou by dou x mu is a covariant vector. This transforms like a covariant vector. So, we consider that as a covariant vector. Similarly, if you consider dou by dou x covariant goes to dou x prime covariant equal to dou by dou a mu nu x nu is essentially equal to a mu nu dou by, okay, let me write it here, taking same argument as earlier. This is 1 over a mu nu dou by dou x nu, which is essentially a mu nu dou by dou x nu. Nu now the subscript, and this is how contravariant vector transform. So, dou by dou x mu is a contravariant vector. So, we will actually denote these two in a slightly simpler notation. Covariant derivative operator dou mu is defined as derivative with respect to the contravariant vector, and contravariant derivative operator is dou mu dou x mu. Right. These are the notations that we will use. When you have the subscript on dou mu, this is a covariant vector like the earlier notations, but then this corresponds to derivative with respect to a contravariant x mu. And similarly, when we say contravariant derivative, it is a superscript on dou, the partial derivative operator, which is equal to the partial derivative with respect to the covariant x mu. And okay, this is essentially equal to dou by dou c t, and minus here you will have actually a c, that it is plus gradient operator dou by dou c t minus the gradient operator. So, here one thing to notice is that compared to the coordinate x mu is equal to c t x, and x covariant is c t minus x. Whereas, in the case of derivative operators, the covariant vector has a plus sign in front of the gradient operator, the special derivative part, and the contravariant derivative has a minus sign with respect to the time component, and this is exactly the opposite in the case of coordinates x mu and x mu, covariant and contravariant. Now, let us come back to Maxwell's come back to the Klein-Gordon equation. Let me call this for short KG equation. So, we have minus okay, so let me write it in terms of c square h cross square second derivative with respect to time or c t minus h cross square c square grad square plus m square c 4 c psi is equal to 0. Please refer to the previous lecture for this. We had written down this. So, now I can take c square h square as a common factor, and then that will give you dou square over dou c t square, which is essentially, let me write it as x 0 square, okay, the 0th element, minus dou by dou x square minus dou by dou y square minus dou by dou z square, okay, psi plus m square C 4 psi equal to 0. This can be written as C square h cross square dou mu, the usual dot product between two vectors. Okay, these are all vector operators, but dot product will give you similar expression as in the case of vector. Psi plus m square c power 4 psi equal to 0. Now, we will work in units of c square is equal to h cross square is equal to 1. Okay. We will work in a unit system h cross equal to 1, c equal to h cross equal to 1, c equal to 1. This is all right, we can do that. This is a new unit system that we are considering, not the SI unit, Lorentz Heaviside unit it is called. And in this unit system, we will have this is basically to simplify our notation, because in relativistic quantum mechanics, both h cross and c will appear in different terms, and then if we put it equal to 1, we do not have to write it, but then the question is whether information is lost or whether we will get confused at any point with the dimensions or with the physical quantities, etc. We will see that consistently at any point, whenever we want to actually recover the h cross and c, where to put h cross and c, dimensional analysis will let us put these in a unique way. Okay. Maybe we will take up some examples to illustrate this later towards the end of this lecture or so. But at the moment, we will take it as that we can, without creating any confusion, we can take h cross to be equal to 1 and c equal to 1 and then work in this unit. Okay. So, in that case, you have dou mu plus m square is equal to acting on psi is equal to 0 is our Klein Gordon equation. Okay. Let us discuss this further. We will consider dou square, write it in a components dou square by dou t square. So, now I will work in units of c equal to 1 square phi minus grad square phi plus m square phi equal to 0. Okay, I change the wave function notation from psi to phi. I mean, no particular need to do that, but let me denote it by phi, because that is the usual the standard way of denoting the fields who satisfy the Klein Gordon equation, or the wave functions who satisfy the Klein Gordon equation. Now, let me multiply this by minus I phi. So, let me call this equation 1. So, 1 times minus I phi star will give me minus I phi star second derivative with respect to time of phi minus I, so plus I phi star grad square phi minus I phi star. Okay, I can take m in the beginning, m outside. So, m square minus I phi star phi equal to 0. Let me call this equation 2. So, let me take the equation 1 star complex conjugate of this and multiply this by minus I phi. So, that will give me minus I phi dou square over dou t square phi star. I have taken the complex conjugate of equation 1 minus, again that becomes plus I phi del square phi star minus m square, only one minus sign there, phi star phi equal to 0. So, this is equation 3. Okay. Now, this equation 2 minus 3 will give me, all right, let me write it here, 2 minus 3 m square terms are identical. So, they will cancel out. Others are minus I phi star dou square phi by dou t square plus I phi dou square phi star over dou t square. Okay. Now, plus I phi star grad square phi minus I phi grad square phi star equal to 0. Now, if I take time derivative acting on phi star dou phi by dou t, that will give me phi star dou square phi by dou t square minus I dou phi star over dou t, there is no I, plus dou phi by dou t. Similarly, for the other term, time phi dou phi by dou t also we can write in the same fashion. We use this to rewrite equation number 4 as, so note that here we have a term phi star dou square phi by dou t square. Phi star dou square phi by dou t square is the first term on the right hand side here. But then that is equal to total time derivative or right derivative acting on both phi star and dou phi by dou t minus, so phi star dou square phi dou t square is what we have in this equation here, the first term on the left hand side of equation 4 apart from the minus I, that is equal to time derivative acting on phi star dou phi by dou t together minus this term, extra term on the right hand side of the first equation here, which is dou phi star by dou t dou phi by dou t. So, that when we put back in equation 4 here will give us minus I phi star dou square phi by dou t square is replaced by dou by dou t acting on phi star dou phi by dou t minus dou phi star over dou t dou phi over dou t plus, okay, we have taken a minus I from the first one, therefore, it will be a plus I phi will become a minus phi now. So, there is a minus sign there because minus I is taken out, and we have again this is phi dou phi by dou t phi star by dou t minus of minus plus dou phi star over dou t dou phi over dou t. So, this is the first term in equation 4. So, this first term in equation 4 is equal to, so let me only focus on the first term, that will give me minus I, these two cancel, the second term and the fourth term cancel. So, that will give me minus I total derivative acting on phi star dou phi by dou t minus phi dou phi star over dou t. Similarly, So, let me call this equation 5. Okay. So, now go back to equation 4. The second term is I phi star grad square phi minus I phi grad square phi star, and in exactly similar way as we did in the case of the time derivative, we can write gradient of minus I phi star grad phi dot here is equal to minus I grad phi star dot grad phi minus I phi star grad square phi. So, the second term in equation 4, which is minus which is plus I phi grad square phi star minus I phi star grad square phi can be written as del dot minus I phi star grad phi, okay, minus I grad phi star dot grad phi. This is for the second term here, minus I phi star grad square phi, and similarly for the other one we have again del dot I phi del phi minus plus I phi I del phi dot del phi star. Again the second and the fourth terms cancel, and then we have this LHS or the RHS here is equal to. So, this is essentially equal to del dot, okay, minus I del dot phi star del phi minus phi del phi star. Okay, so essentially what we have done is we have taken this equation 4 and written each of these term as a time derivative for the first term acting on both phi star and dou phi by dou t. Okay, time derivative is acting on both the terms, both the factors there, and similarly for the gradient we have rewritten that in a more in a different fashion. Why we are doing it? Because when we write it so, we have essentially equation 4 will give you time derivative I star phi star dou phi by dou t minus phi dou phi star over dou t. Okay. So, this is basically what we have from equation 5 here, and similarly from, let me call this equation 6, from 6 we have plus del dot minus I phi star grad phi minus phi grad phi star. So, equation 4 can be written as time derivative of some term plus divergence of something else is equal to 0. I will write this in a compact way as dou by dou t of some rho plus divergence of some j equal to 0. So, this is one thing, and now where rho is essentially as is rho is equal to I phi star dou phi by dou t minus phi dou phi star over dou t, and j equal to minus I phi star grad phi minus phi grad phi star. So, this thing here is a very compact notation, compact equation. You must have seen such equation in the earlier discussions at under different topics. This is what is called the continuity equation. Okay, just before we come to that interpretation of this, I can actually write a more compact current J mu with component rho and j vector, and the continuity equation dou by dou t of rho plus divergence of j then becomes equal to 0, then becomes dou mu j mu equal to 0. You notice that between the spatial and the temporal components here, the 0th component and the 1, 2, 3 components, the sign is not minus but plus. Just as an aside, x mu we had x 0 minus x dot x. This was also the case where we had the operator dou mu equal to dou 0 square minus grad square, relative sign. But here we do not have that relative sign, because dou mu is dou by dou t plus grad. The covariant vector has a plus sign in this case, and j mu is a contravariant vector which also has a plus sign the way we have defined j. So, this is the continuity equation written in a compact way. The physical interpretation is that, all right. So, this is the continuity equation. If you look at the expression here in 8, equation 8, j is something which we had already familiar with in the case of non-relativistic quantum mechanics. Okay. So, there j is basically considered as the probability current. So, this here again we can interpret rho as the probability density, or rate of rho is the probability density and j is the probability current. The interpretation is this, that if you consider a small volume, say a small cube, rate of change of probability density inside the volume is the same as the rate of change or the divergence of the j, which essentially is because of the divergence theorem or the Gauss's theorem. This corresponds to the flux going out of the surface from the volume, this thing. So, minus of this thing is actually the flux which is going out of this volume. So, it essentially says in words that rate of change of the continuity equation will tell you the rate of change of probability density rho inside the box is equal to flux. Flux is j dot the area. So, you have to use the Gauss's theorem, divergence of a vector over integrated over a volume is the same as j dot dA, the surface integral of the same vector over the closed surface which encloses the volume or the boundary of the volume. So, that is basically the flux. The right hand side here is the flux of this thing, of the field. So, here it is the flux through the surface of the box. And what flux is this? The flux is basically the probability flux. So, it says, for example, if you consider some number of particles inside this one, then it will actually tell you the rate of change of the number of particles is equal to the number of particles that flows out, or the probability for the number of particles to flow out. So, it's a kind of a statistical statement. That is what we expect in quantum mechanics, but it essentially is very similar to the continuity equation that we have in any other physical situation like fluid dynamics, water flow or liquid flow. All right. Now, so we have the expression for rho equal to I phi star time derivative of phi minus phi time derivative of phi star. This is the probability density. So, the probability density. If I take a plane wave solution or plane wave for the phi, then I can write it as e power I p dot x minus I energy times time. This is a plane wave. Then rho is nothing but I phi star remains as phi star. Dou phi by dou t will take out minus I e and then phi itself minus phi as it is. Phi star now will have a n star exponential minus I p dot x plus I e t. So, when I take the time derivative, it is plus I e that comes out and then phi star as it is. This is, so there is an I here overall factor and then there is an minus I e in the first term. Together that will give me a plus e. So, plus e, and in the second term again I have a minus sign. So, minus I e inside the bracket and an I outside. So, that is again going to give you a plus e. So, total 2 e phi star phi, which is 2 e n square mod n square. So, rho in the case of plane wave solution is twice the energy of the solution wave function and or energy of the particle corresponding to the wave function and the normalization square. All right. So, now let us consider the phi we said is a phi equal to n e power I p dot x I p dot x minus I e t is a solution of Klein-Gordon equation. Dou square phi by dou t square minus del square phi plus m square phi equal to 0. If this is so, then phi equal to some other phi or phi prime, or let me take some phi prime n e power I p dot x plus I e t. This is also a solution. That is because the equation Klein-Gordon equation is quadratic equation. It is actually second order derivatives are coming in. Therefore, I plus I e square and minus I e square both will give you the same minus E square. So, essentially this is coming down to the situation where we have to start with, we have P square minus, okay, let me write down, both of this actually give you, when you put it back in Kg equation, Klein-Gordon equation, both of this will give you E square phi minus P square phi, sorry, there is already a minus sign there, plus. So, this is minus, this is plus, m square phi equal to 0. Okay. Both of this will give you this. So, this is essentially E square is equal to P square plus m square, which is basically the energy momentum relation, relativistic energy momentum relation. And if I write down the expression for E, I can actually write it as P square plus m square under root plus or minus. Now, we can see that more clearly. If whether I take plus E or minus E, the equation should give the same result, or the other way of saying it is that E is a solution to this thing, minus E is also a solution. I mean, expression with plus E is a solution to the Kg equation, expression with minus E is also a solution to the Kg equation. When we interpret E as energy of the particle corresponding to the wave function phi, this then put us in a difficult situation. It tells you that you have a solution with energy E for this particle, and you cannot in that case avoid a solution, another solution with minus E. So, a negative energy solution emerges, comes along with a positive energy solution. This is a problem because we are talking still about free particles. We have not put any potential here. These are all free particle solutions. We do not have any extra potential. That is why E square is equal to P square plus m square. Only the kinetic energy term and the mass term are there in the energy. So, negative energy is not a physically viable case. We do not want to have negative energy solutions, but the Klein-Gordon equation actually gives you solutions with negative energy. So, this is one problem. So, problems with Kg equation as it stands now are: 1 negative energy solution, 2. For that, let us look at the probability density. In our case, the probability density is equal to twice the energy times n square. N square is not positive, not negative, 2 is not negative. So, if E is negative, then rho is negative. So, that will give you for E less than 0, rho less than 0. How do we interpret rho then? As probability density. So, difficulty with interpreting, or let me simply write it as probability density. We cannot have negative probabilities, which is physically not valid. So, these two problems are to be addressed to understand the relativistic equation, relativistic dynamics of particles through Klein-Gordon equation. We will come to how we actually address these questions in the next lecture.